Let's use a dictionary to demonstrate the binary search. This dictionary has roughly 1,200 pages in it, goes all the way to page 1164. And so the claim is, in roughly 1,200 pages, we can find any word that's given in 11 comparisons or fewer. And there's a reason for that number, and I'll explain afterwards. So at one of the workshops I did recently, the word serendipity was suggested. So let's try to find the word serendipity. You always go to the very middle of the book first, and that is the first division. The words go from mystery play to narrow. Clearly, serendipity is going to be on this side of the list. We do a search number 2, and the words go from story to strategy. Serendipity is going to be over here. This was our second search. In our third search, it goes from reduction division to refractor. Clearly, serendipity is going to be after the word refractor. In the fourth search, the words go from sex chromosome to sham. Serendipity is going to be over here. This is our fifth division, and this goes from sales register to Samite. So serendipity is going to be over here. This goes from scrutinize to seals. Serendipity is going to be over here. This is the seventh search, which goes from semi-nomad to sensualist. Serendipity is going to be over here. This is our eighth search, which goes from serfdom to session. And so serendipity is going to be over here. And our final 2 pages are between sensualistic and serf. Serendipity is going to be right there. We found it in 9 searches. Now that you've seen the binary search in action, let's take a closer look. The most important thing to understand is that the list must be in order for this process to work effectively. The idea is, of course, to look at the middle to see if you have a match. If you don't, you go to the left if the target is less. Otherwise, you go to the right. And you keep doing this until you find the item or there's nowhere else to look. Here's the pseudocode. Basically, the idea is to return the value where you found it or return a -1. We have the list and the target. We start the left at position 0, the left edge, and the right at position list length -1, the right edge. And as long as left is less than or equal to right, we still have values to look at. We find the middle value. If it matches our target, we return the middle and we're done. Otherwise, if it's less than the middle, we go to the left. Reassigning the right value to middle -1 does that. Otherwise, we go to the right. Reassigning left to middle +1 does that. So this process continues while this condition is true. Let's work through an example. Now the answer to this question is pretty easy. Where is the 3? Well, conveniently, we have a list from 0 to 20, and all of the values are in their actual position. 0 is in position 0, 1 is in position 1. The answer to this one is 3. But that's not the crucial question. The question is, how many steps did it take to find the 3? Well, the binary search process first finds the middle position, which is position 10. Is 3 a match for that? The answer is no. So we go to the left. The new middle position is going to be the 4. Does the 3 match the 4? No, it's less than that. So we again go to the left. The new middle position is the 1. Does the 3 match the 1? The answer is no, it doesn't. So we go to the right. The new middle position is the 2. Does the 2 match the 3? No. So we go to the right again. And now that's the new middle, and it does match. So it took us 5 steps to find the 3. Here are 2 examples for you to try out. Pause the video and see if you can figure out the number of steps it takes to find the 16 and to find that the 21 is not there. Let's work through it. Now the answers are clearly 16 and -1. But the question is, how many steps does it take? We start out the same way by looking at the middle position. Is the 16 equal to that? The answer is no. So we go to the right. The new middle position is the average of 11 and 21. So that's 31 divided by 2, that's 15. There's the new middle position. Is the 16 less than, equal to, or greater than that? It's greater, so we go to the right again. Now the new middle position is 18, because 16 plus 20 is 36. Half that, we get 18. Where is the 16? It's to the left. Now we find a new middle position, and it is indeed the 16. It took us 4 comparisons to find the 16. Now, what about the 21? How many times will it take us to discover that the 21 is not there? Well, let's check it out. Again, we start at the 10, because that's the middle. 21 is greater than that, so we go to the right. Then we go to the 15. 21 is greater than that, so we go to the right again. 18 is the new middle number. Still greater than that, we go to the right again. 19 is the new middle number. Still greater than that, we go to the right again. 20 is the new middle number since there's only one value left to look at. It's greater than that. So we step to the right, but now since the left and the right markers have crossed, the right marker is still there, here's the left marker, the code is basically saying we're done here. The left and the right marker are no longer in relative position with each other. And so the final answer is a -1, meaning it's not here. Now let's do some analysis. The basic idea behind the binary search being a divide and conquer process means it's going to have a basic runtime of log n. But the best case scenario will be O of 1, because that's when you find it right away in the first middle position. Otherwise, the average and the worst case, even though you don't find it, it's still going to be a log n process. Now let's talk about the 11 steps that I claimed in the dictionary search process. Why did I say 11 steps? Well, as you recall, we had roughly 1,200 pages in the dictionary. And in the powers of 2 table, the value 2048 is just past 1,200 pages. And therefore, we can use 11 as the log value for that. That means that in a binary process of any kind, including this binary search, 11 is the number of steps it takes at most to accomplish the task. That's why I claimed that I could find the word in 1,200 pages using 11 or fewer steps. And as you recall, it took us only 9 steps. In the array example that we had 21 items, 32 is the value just past 21, which has a log base 2 of 5. And that represents the most number of times that it took us to either find an answer or to discover that the value wasn't there. Again, a log n process. So in summary, be sure you understand the basic process of the binary search. Look at the dictionary demonstration that we showed. Look at the code again, and be sure you completely understand what's going on with the binary search.